Hi everyone, my name is Neha and this is the 13th lecture on Introduction to Automation. In this lecture, we are going to learn about direct current motors. Motors, they are the actuators which converts electrical energy into mechanical energy, and they are classified into two types. First is the AC motors, and AC motors, they are also called alternating current motors, and the second one is DC motors. DC motors stands for direct current motors. Let's see some of the advantages of these types of motors. So in case of AC motors, they have the low startup power demands. They have controllable starting current levels and acceleration. In AC motors, you can add a VFD, where VFD is the variable frequency drive you can add that can control the speed and the torque at different stages of the use. In AC motors, it is more durable and it has a longer life. Whereas DC motor is very simple to install and has a easy maintenance, and it has high startup power and torque. It has fast response time at starting, stopping and acceleration. It has availability in several standard voltages. So these DC motors, they have speed control capability, which means they can control the speed, torque, and even the direction of the rotation can also be changed in this type of motor at any time to meet the new conditions based on the application. Now let's see where these two types of motors can be used. First, let's start with the AC motors. So the AC motors, they can be used in appliances like fans, computers, conveyor belts. They can be used in air conditioners, in hydraulic pumps, etc. Whereas the DC motors, they are used for fabrication and production units. They are used in the machines that demands constant power, for example, vacuum cleaner, elevators, sewing machine, etc. They are also used in warehouse for sorting the equipments. And here on the right, you see the picture of a AC motor, and this is the picture of the DC motor. Now let's understand the theory of operation of DC motors. The DC motor, it converts the direct current into the mechanical work, and it works on the principle of Lorentz law, which states that when a current carrying conductor is placed in a magnetic field, then a force is induced on it. So as you can see here, this is the experimental setup where a magnet is there, and in the under the magnet we have this conductor, and in this conductor we are supplying the power. So with the help of this power, the current will start flowing into this conductor wire. So once the current starts flowing into this conductor wire, then due to the effect of this magnetic field which is created by this magnet, you can see these are the magnetic lines of forces. Due to this effect, what will happen? A force will be produced on this conducting wire. So this is based upon the principle of Lorentz law. On the right hand side, you can see the direction of the force, magnetic field and the current, which is represented using the right hand, where the thumb represents the direction of the force and index finger, it represents the direction of the current, and the rest of the fingers, they represents the direction of the magnetic field. So you can see here the force is perpendicular to both current and the magnetic field, and the force can be represented by this formula which says F is equals to IBL sine theta. So where I is the current through the conductor, and B is the magnetic flux density, and L is the length of the wire. And this angle theta, it is the angle between the magnetic field and the current. Now let's see the DC motor action. So here on the left picture which you see here, this is the brushes. These are the two brushes which are connected to the commutator. In this commutator it rotates, whereas the brushes, they are the stationary part of the motor. And then you see here this wire, this is the conductor in which the current will flow, and then we have the magnets which are placed in this way, So this first picture shows that when you give the supply, DC supply, through these brushes, then what will happen? The current will start flowing from here, and this will be the direction of the current. And you can notice that due to these two magnets, the magnetic field is created here. So we have a conducting wire which has a current flowing into it, and then we have a magnetic field. So due to which, what will happen? A force will be produced. So you can see this will be the direction of the force. And this direction we have got when the current is flowing in this way. Whereas when the current flowing in this direction, then the force will exert downward. And the direction of this force you can also determine by using the Fleming's left hand rule. So this is the by this left hand rule we can determine the direction of the force. So if the current is flowing in this direction, so this middle finger represents the direction of the current, and index finger represents the direction of the magnetic field, and thumb represents the direction of the force. So if the current is flowing in this direction, then the force will be exerted in this way. So same principle is applied over here in the DC motors. So in this picture you see the current is flowing in this way. So right now our coil A, this is a single wire, but we have named this terminal and this side differently. So this is A and this is B. So in the first case, this A wire side is going to be on this side, and B is on this side. And in the second case, what will happen? Due to the force, what will happen? This coil will move. So when this coil will move, then this B wire, it will go to this direction, and this A will come to this side. So you can see that in this picture that A side of the wire is here, and B side of the wire is here. Now, to reverse the direction of motor, the polarity of the voltage here to the commutator is reversed, and this will provide the force on the armature coil you see here to be reversed, and the motor would then run in the opposite direction. Now, if you run the motor with this one single coil, then what will happen? The motion will be irregular. So the motion will actually is not going to be very strong because you will have just one coil. So to avoid that problem, or to resolve that problem, what you can do, you can add more loops. So you can add more number of coils here, and for that you need to also have more number of commutators. So let's see how the arrangement will look like. So as you can see here, this represents different numbers of commutators which are attached to the coils. So in this particular case, if we see, we have 3 coils attached. So this is the one coil, and then we have another coil over here, and then third coil is like this. So by this arrangement, you will have better force on the armature coils, and your motor will rotate more fast when compared with only single conductor. And if you use a high permeable steel layer inside these wires, then what will happen? An enhanced magnetic flux interaction will take place, and due to which the force exerted on the armature coil will be more, and your motor will basically move more smoothly. Now let's see this with the one coil, how it will look like. So this is our DC motors. You can see the direction of the force, how it changes every time it moves. Now let's see here, when you have 2 coils attached to the brushes, you see here there are 2 commutators which are used, and then you have 2 coils. Now let's see the effect. You can see at one time one of the coil is getting the power from the supply, but due to the interaction of the magnetic field, the force will be exerted on the other coil also, and it will provide the movement. So this is again is not the practical DC motor. If you see the practical DC motor, it will have more number of conducting wires. So these conducting wires, or we can say that the coil, they are made up of iron, copper, or aluminum. Now let's see next. Now you can see here in this picture that multiple armature coils are used, and they are fitted inside the highly permeable steel layers, and this steel layer is used to enhance the magnetic flux interaction. And here on the right, an electromagnet is used on top of this arrangement. So here inside you see that these are the armature coils, and then you have the steel layers, and then on top of it you have this electromagnet attached to the field coil. You see these are the field coils, and through these field coil you will provide the DC power. So this type of arrangement is used in the large motors. Now let's see next the torque equation in the DC motor. So the torque is given by this equation which says Kt, Ia, and phi. So this Kt, it is a constant which is based on the motor construction, and Ia is the armature current. Armature current is the current flowing in the armature coil, and this phi is the magnetic flux. So by this we get the motor torque equation. Now next we have the back EMF, and this back EMF is the electromotive force which this EMF stands for, and this electromotive force is produced in the DC motors when the conductor it cuts the magnetic field. Then this EMF will be induced in the conductor, and the direction of this EMF produced will be opposite to the applied voltage in the DC motor. And so this back EMF it will be given by this formula Ke phi s, where K is the constant based on the motor construction, phi is the magnetic flux, and s is the speed of the motor. Now next is the actual voltage equation in DC motors. So here you see the actual voltage equation which is given by this VA is equals to VLN minus CEMF, where VA is the actual voltage which is available to the armature, and VLN is the line voltage which is supplied to the motor, and CEMF is the counter EMF. And this VA has been further written as in terms of current and the resistance. So you can write it as IARA, and RA has been taken here. So by this we get the armature current equation. So here you can't actually directly measure the VA with a voltmeter because it's an effective voltage inside the armature, but there is a physical evidence that back EMF exists because of the armature current, because we see that the armature current it gets reduced. Here we see the relationship between the back EMF, motor speed, armature current, and the torque, and we see that as the back EMF it increases with motor speed, as the motor goes faster, then what will happen? The less current motor will draw, and in that case your torque will go smaller, or it will diminish. So this explains why most DC motors they have finite maximum speed, and if the motor keeps on going faster, then what will happen? The back EMF cancel out the line voltage, and armature current will approach to zero. Now let's see the formula for speed. So this has obtained from the formula of back EMF, and you can see that S is the speed which is equals to counter EMF, or we can say that the back EMF upon Ke, which is the motor constant, and phi is the magnetic flux. Now next is the speed regulation, and the speed regulation, it can be of a DC motor, it can be defined as the change in speed from no load to full load, and it is expressed as a fraction or a percentage of the full load speed. So you can see here it is given by this SNL minus SFL, where SFL upon SFL into 100, where SNL is the no load speed and SFL is the full load speed. So if the load is applied to the DC motor or machine, then the speed of the motor, it will decrease automatically, and thus to maintain the constant speed, the difference between the no load and the full load speed is basically called R, speed regulation, and it should be maintained very less. Now let's see a problem on a DC motor. So this problem says a motor generates a counter EMF at a rate of 0.4 volts per 100 RPM and has an armature resistance of 20 ohm. 10 volts are applied to the motor. Find the armature current just after the power is applied and when the speed is 1500 RPM. So armature current is given and 0.4 volts of back EMF is given at 100 RPM, and then you have line voltage which is 10 volts here, and then you have to find the armature current when the speed is 1500 RPM. So back EMF is given at this RPM, and then with this and then you have this 1500 RPM. So you can find a relationship between these two, and by that you can calculate the back EMF at this RPM speed. So you have all these things which are given, and then you have this back EMF at 1500 RPM, which you can calculate by this ratio formula. So if you do the calculation, you will get 6 volts, and then at 0 RPM you can find out the armature current. So putting the value of line voltage, which is 10 volts, and counter EMF is at 0 RPM is going to be 0, and this RA is 20 ohm. So you will get 0.5 armature current. So this is at 0 RPM. Now let's calculate at 1500 RPM. So you will use the same formula. Line voltage is going to be the same, so 10 volts. Counter EMF at 1500 RPM, it's going to be 6 volt, because we have already calculated above, and then this whole is divided by the armature resistance. So if you do so, you will get 0.2 ampere. So this is the solution of this problem. So this is the end of the lecture. Thank you so much for watching.